Hello, this is a demonstration of my 8-bit computer. Well, it's a CPU, not a computer, and the utilities I have set up for it. So, first, I'll show you the instruction set and the register map. So, this is an instruction set consisting of no op, so no operation, read a register to the bus, write to a register to the bus, set, which sets the bus to a value. JZ jumps if the bus is 0, JNZ jumps if it's not 0, JMP jumps to a location regardless, JBU jumps to whatever's on the bus, RCA reads the ALU carry to the bus, HLT halts and waits for an interrupt, PCI increments the program counter, returns to the microcode stack pointer, call will jump to a location, set the microcode stack pointer to the address after whatever that instruction address is. So the next address, in short. And then the last three are really just for debugging. But I mean, yeah, you could use them to optimize something, but yeah, you really wouldn't want to do stuff at that low level. So here's your ALU registers, 0x10, that's the range for that. For any ALU register, so anything that starts with 0x1, and then anything that's a microcode register, it's 0x2. Anything that's general purpose, 0x3. Anything that's cache is 0x4. And anything that's debugging, 0xf. And there are certain sets of microcode registers, and when a PCI is called, so when the program counter is incremented, um, these first four registers are all reset to 0. But the other four after it are completely persistent. And then the microcode instruction pointer is, well, reset whenever a call statement is issued, or whenever the computer is turned on and off again. So I'll go through the ALU opcodes too, so you can pause if you want to look at it. I also wrote a compiler for it, and I will show you a syntax file for that. So if you're interested, you can pause it and look at this. And now I will go into some example programs. So this is a Fibonacci sequence using the microcode assembly, and basically, well, I mean, it looks a lot like the actual, it's a direct translation. So what we're doing is we're saying the add opcode and we're writing that to the ALU opcode register. Then we're saying 1 and writing that to ALU registry A, saying it to 0, and we're writing to ALU registry B. Then we're reading the result, and then we're writing that to the debug so we can see the progress. Then we're writing that to ALU registry B, and then we RCA. That returns a carry. So if the carry isn't 0, we end. So that halts and program counter increment. So read result, write debug, write ARA, RCA. If the carry's not 0, stop, and otherwise just go right back up here. So that's a really basic fib sequence, and I will demonstrate that in action now. So after the software set, I will go into the hardware. And I have pre-compiled these, which is convenient. So I'll go ahead and start, and as you can see, the debug registry is doing the Fibonacci sequence. I'm going to increase the tick rate a bit. Yeah, so it's fairly fast. Before this video, I had a bunch of problems. For some reason, I'd wired the clear to the read on some of the registers. Don't know what I was thinking. So this is just some, so this is multiplication. And this is the results. A value repetitively decremented, B value repetitively added to LMR2. LMR2 is the result, LMR3 is the overflow. The add opcode, subtraction opcode, greater than pass, and the less than pass, some are all opcodes. And greater than pass and less than pass basically say if A is greater than B, then pass A. Or less than passes if A is less than B, then pass B. Or I mean, if A is less than B, then pass A. Or pass whatever is the lesser number. And pass whatever is the greater number. And they're really convenient because then you can optimize your code accordingly in the case of this because it's repetitive addition. So this just asks user input from this entry panel here. I'm going to just set it all to zeros. And then it clears ILMAR2 and ILMAR3. Not really necessary, but I said why not do it, and I've done it. So this checks if either registers 0 and then just ends it, because there's no point in continuing if either registers 0, because 0 times anything is 0. That's a little optimization. And then this compares the two registers and puts whatever's smallest in ILMAR0. That's their counting register, and it's the one that's actually counted. So it increases the speed by counting less. And it's repetitive addition again. So this loop here, decrement ILMAR0, it reads whatever's in ILMAR0, subtracts 1, so as you can see, and then reads the result and rewrites it. So that's just decrements. Then adding ILMAR2 to ILMAR1. So this just adds whatever's in ILMAR1 to ILMAR2. So it increments ILMAR2 by ILMAR1. And it's pretty straightforward. And if there's overflow, so we jump into overflow skip if there is no overflow. So if there's no overflow, we skip all this code here by jumping right to here. Otherwise, we're going to write to ARA. We're going to read ILMAR3. We're going to write that to ARB, and it's already set to add. And it's going to read the result and write that to the overflow register. And then if ILMAR0 is 0, then end the program. Otherwise, continue. jz.end, and yeah, jump loop. So back to the beginning. And then, now for the ending, read ILMAR2, write debug, read ILMAR3, write debug, halt, and program counter increment. So we'll go ahead and see that in action. So clear the register, and first we'll try something simple. So 2 and 4. So as we can see, the debug register just counted up to 8. So now we'll try 8. Well, might as well 10, interrupt, and 2. So as you can see, 10, 20. So as you can see, it only counts 2 times because 2 is the lowest number, and logically it should count by that instead of counting by the highest number, which would take more clock cycles, and that's no good. So we'll try something a little bit more complex, something that would have overflow, like 13. Yeah, and 49. So interrupt, and we'll just go ahead to increase our speed here. As you can see, we get 125, and if we clear this, so that's the correct result. So that's 13 times 49. I'll just go ahead and prove that. So if we add 125 plus 2 times 256, because this is a high byte, so you have a high byte and a low byte, and then the low byte was 125, and then the high byte is 2 times 256, which is 512, and we get 637 as per expected. So that's a multiplication, and I might have a little bonus for you. You just make sure. This is a call test, but I won't go into that. I've tested call before, and it does work. Basically, all it is it's calling. So, you know, might as well show you it working. Yep. Okay. Ooh. Oh, I called it call test, not contest, yeah. So we'll just load that image right up. Clear it. And, well, yeah. So I assume that's probably the correct, what was expected from call test, and we can look at the code. Okay. Yeah, so it's adding 8 and 4 in it. So it's setting 8 and 4 and then it's adding them with the add coroutine. So as you can see, yeah. Hmm. Well, that code is bugged, but I won't get into that, so don't even worry about it. Anyways, let's go to our next part. So registry, cache. So I'll show you the hardware. This is the MCU. This is where all the magic happens. Register, select, and basically we have read, write, whether or not the register should be selected in general, the location of the value for the register select, which is where cell becomes in that instruction. Um, there's a register read and a register write. These are global register reads, register writes, and a register select. So if this is high, it's going to read from whatever register is selected by this value. If this is high, it's going to write to whatever register is selected by this value. And the register select, as you can see, it can either come from the parameter or the bus in, and that is dictated by the celb instruction. There's also a GRD and a GWR, which just directly set these two values. There's not much of a reason to do that, but yeah. So register select, that just dictates whenever this actual register is high. And when that register is high, the value is scrap. This is our bus output, and that's only actually a value certain times. That's only a value at certain times. So it's not to worry. This right here is a bus output register at this particular of the MCU. So the MCU has the ability to inject data onto the bus directly, and with that ability, well, it needs its own register. But this has no value. This has no register select register. It can directly set or unset the bus accordingly. This is a halt. This is the interrupt thingy. So when you perform a halt instruction, it sets this to low. It resets this flip-flop. And when that's low, it waits for the interrupt to set to high. This is our stack pointer. So when we do a call, it stores the next address into here. As you can see, I'm just adding it with the constant O1. And if the current address is FF and the next address is 00, the next address would be 00. I will eventually consider implementing something to handle that because I just realized that's probably a problem. Anyways, that'll probably become a problem later. So what does this do actually? Well, this checks if the bus is 0 to dictate whether or not it should jump. So this is a jump OR gate, and if any of these instructions are present, then it's going to jump. And the actual commands there are the microcode address, the microcode jump. And the microcode address can be the bus, or it can be the stack pointer, or it can be the parameter, whatever. Anyways, so we'll go back to the CPU. And then the MCU has the main bus. The main bus is connected to everything. So the ALU has its own main bus, registry, cache, debug. These are just bus read, bus write devices. This is a separate FF. So this is register FF. And This is also register FF. If you're wondering where these special components came from, they're from Logisim Extended, which which if you need a link to or you would like to use in one of your projects, ask me and I'll send you a link to my GitHub page where you can download it. And if you're wondering what's in it, there's screens. So, I mean, this is a actual 256 by 256 screen, and color screen, binary to BCD, up to 32 bits. We'll just undo that there. So yeah, I'll show you that. It's quite insane. So yeah, and also, so you can reverse the number, or you can offset for 7 sec. You don't need to. It's not required. And you can just have 32 outputs like insane person would. This isn't in the current version. That's just me testing. I'm just gonna reset simulation, re-enable. There we go. Hey, work you. Oh, I think it broke it. There we go. Oh yeah, look, ew, it's really broke. Yeah, so we'll just wait. Was that my plugin? Oh, hey, look, I got a bug. And just sort that out soon here. Anyways, from that little distraction, this is the ALU. ALU pretty self-explanatory. All this is logic gates and the arithmetic unit. This is a greater than, less than, pass functions, and then if it's equal. So that's all they do. Wait, no, that's actually handled in the arithmetic, I think. Uh, oh yeah, it's handled in the logic. So correction. These do something else, and I don't remember what they do, to be honest with you. Oh, this is selecting which device it should receive the carry out or borrow out flag from. Duh. Yeah, so there's borrow out, carry out. It's the same thing, same flag. Anyways, so here's the ilm counter, microcode counter, the register buffer entry, and then here's the cache. So it's a pretty simple little CPU, nothing too complex. I do want to, in the future, add support for a screen, which would be pretty cool, and some kind of big addressing scheme. So rather to being only 8 bytes of address, I want some form of way to address something like a 4 GB SD card. And in order to get that to work, I'll probably add a custom component here, like hard drive, where I can set the. So the problem in Logisim is that there's no real form of persistent storage. So there's RAM and there's ROM, but there is no hard drive. ROM is only read-only. RAM, well, when you restart the program, you lose everything. So, yeah. I want persistent storage, so I can keep data forever. But that's a future thing. Anyways, in terms of how this thing works, pretty simple. The interrupt I recommend you could hook it up to a counter on the clock so that it interrupts every X amount of times. And one of the future improvements I want to make is an interrupt ID register so it can figure out why or what caused it to interrupt, as well as maybe even have support for software interrupts and different interrupt types, of course, because just stopping the clock is relatively stupid and not very practical. And Yeah, if you just stop the clock, that's not necessarily going to be good because it might never be started again. So yeah, I'll demonstrate the compiler here too. So if you are interested in the code, it's horrible. But if you want the compiler code, I can send that to you. And here's the actual register map used by the compiler, and here's the instruction map used by the compiler. So that's the instruction map. Here's the register map. And as you can see, there's a lot of them. And each of these has to be individually coded. If they're not, well, that's a problem. You have to individually code each one, otherwise it bugs out. You wouldn't want it. It wouldn't know. I don't have any support for a way to specify a range of registers. So I can't do something like A star equals 0x30 to 0x31. Or correction, A star would equal 0x30 to 0x33. Or Ilmar star is equal 0x20 to 0x27. I could add that, but I probably won't ever get to it. Oh, and the cache is addressed by an address register, and well, you set and unset the value in cache from the data register. So, pretty simple, pretty self-explanatory. See it, like, favorite, subscribe, whatever, or dislike, your choice.